Hello, this is Dr. Viv. Let's try to solve a problem involving friction. The problem states that it takes a block 3 times more time to come down an incline than it does to go up an incline. Determine the coefficient of friction mu sub k. You're given the angle is 30 degrees, but you're given nothing else. So how do we solve the problem? Well, the only trick in the book is to proceed systematically and do a free body analysis. So I'm going to draw the free body diagrams. The appropriate free body axes are going to be tilted. I'll draw them both simultaneously. That's going up the incline, but even though it's going up the incline, the acceleration must act in the downward direction because it's eventually slowing down and coming to a stop and then returning the same way. When it's returning, it is speeding up from 0, but we don't know what direction it would be. The acceleration would be, if it's going to be in the forward direction or the backward direction. It could be slowing down or speeding up. We don't know. So we'll just assume it has to be speeding up because it starts from 0. So we'll assume that it actually is in this direction. I'll call this A2. All right, let us write the free body diagram based on that. I always like to take my x-axis in the direction of the acceleration. Now let's draw the forces acting on the object. You have the normal force, the force of friction. In this case, since the block is going up, the force of friction is going to be opposite the direction of instantaneous motion. I'll call this FFK1, and in this case the force of friction is going to be in this direction. FFK2. And then you have the weight of the object, which always acts vertically downwards with this angle theta here with the vertical. And then I always like to also draw the force table. I'm going to draw a simplified force table where the forces are self-identified by the symbols you give them. So that's X, that's Y, normal force, the force of friction, and then gravity. You notice that the adjacent side, which is cosine, is in the negative y direction, and the opposite side, which is sine, is along the positive x direction. Let's repeat the exercise. Gravity does not change. So in this particular example, I'm going to get the same gravity components. Friction does change. The friction, the way it changes is that you have negative FFK2, not 0, and the y component is 0, and the normal force remains the same. So once you've filled up the force tables, you then go about writing Newton's laws. We'll do that here. Newton's law for the first block is the sum of all the forces in the y direction equals 0 because the blocks don't fly. Again, I'll do them for each block separately, but side by side. So let me just divide the page here. So that's block M1. And well, that's the block on the way up. And that's the block on the way down. Sum of all the forces in the y direction, which is MAY, is going to be 0. So I'm going to get Fn equals mg cosine theta from this. Exactly the same on this side. What about the x direction? Sum of all the forces in the x direction is mass times acceleration ax, which in this case is a1 according to my convention here, a1 and a2. So let's proceed with that. Look at all the x forces. It's this plus this. So ff k1 plus mg sine theta is equal to ma1. On this side, I'm going to get negative ffk2 positive mg sine theta is equal to ma2. Well, that looks good, except we don't have a way of relating the x and y directions. That is provided by the law of friction. The law of friction states that the force of friction is mu times a normal force, in this case mu k. Let's write down the law for here. It's going to be so it looks like the force of friction is going to be the same for both the up and the down phases. And so I'll just write one equation. F sub fk1 is equal to mu k times mg cosine theta, and that's also going to be equal to f of fk2. So now we have all our ingredients. Let's try to put this in that equation and solve. I'll call this equation 1 and equation 2. From equation 1, I get mu k mg cosine theta plus mg sine theta equals ma1. And from equation 2, I have negative mu k mg cosine theta plus mg sine theta is equal to ma2. Observe that mass cancels throughout, which means that it doesn't matter what mass goes up or down. The first acceleration a1 is going to be g times mu k cosine theta plus sine theta. And the second acceleration a2 is going to be g times sine theta minus mu k cosine theta. So you can see the acceleration on the way up is greater than the acceleration on the way down. So it makes more sense for the particle to take a longer time to come down than it does to go up In fact, the problem says it takes 3 times longer to come down the incline. Well, now that's the last phase of the problem. We have to connect using the information of acceleration with one-dimensional kinematics. Even though the problem looks 2D, it's actually 1D because along the direction of the incline is one-dimensional. Let us look at the kinematical equations to use in this problem. They're going to be the kinematical equation, which I like to call 2. So the kinematical equation 2 should be used in this problem. Let's write the kinematical equation 2 down. It is x equals x naught plus v naught xt plus 1/2 at squared. That's the kinematical equation in general. Now what we need to do is use it in this problem. On the way up, the particle starts from a 0 position and goes all the way to the position which I'll call L. That's the length of the block we're assuming is L, or the incline is L. And on the way down, it starts from L and comes to 0. So we're going to take our 0 to be the bottom of the incline for both problems. Let us solve the kinematical equations 2 for both the problems. I'll do it here, one below the other. So for the way up, the final x is L, the initial x is 0. There's going to be some initial velocity, we don't know what it is. Minus 1/2 a1 t1 squared. I'll call this t1. The kinematical equation for the way down, the final is 0, the initial is L, the initial speed is 0 because starting from rest on the top, and then it's going to be plus 1/2 a2 t2 squared. Now because I have chosen my initial velocity to be L and the initial position to be L and the final position to be 0, I actually have to put a minus sign here for the acceleration. If I put the plus sign, I have to take the absolute value of this. It really doesn't matter. Let me continue putting the plus sign. So I still have to find out what the initial velocity is. That is something you have to do separately. So the kinematical equation 1 can be used for that. On the way up, we have v equals v naught minus a1t on the way up. Well, the final velocity, v final, is 0. So I'm going to get that to be 0. This tells me that v naught is actually a1 t1. I can put that in this equation. I get L equals a1 t1 minus 1/2, well, a1 t1 squared because it's a1 t1 times t1 minus 1/2 a1 t1 squared. So that's going to be 1/2 a1 t1 squared. And here I'm going to get L equals negative 1/2 a2 t2 squared. All right, we are ready to now substitute all the values. a1 is given by that and a2 is given by that. So I'm going to divide these two equations. If I divide the two equations, I'll get L equals 1/2 a1 t1 squared, but it's also equal to negative 1/2 a2 t2 squared. So if I cancel out the halves, I'm going to get a1 over a2, negative a1 over a2 is equal to t2 over t1, the whole thing squared. And that in our problem is going to be 3 times. So that thing is going to be 9. Okay. Now let us solve for the coefficient of friction. So for that, you would need to put a1 and a2. Because I have a negative sign, I'm just going to flip the order of g sine theta and mu k cosine theta. I'll flip them as I write it. So the last, therefore, a1 is that. So I get mu k cosine theta plus sine theta. G cancels out. So this thing is planet independent, divided by, and because it's a negative sign, like I said, I'm going to interchange it. So there's going to be mu k cosine theta minus sine theta, and the whole thing is equal to 9. I'll put the theta value at the end. Now we have to solve this, so I'll cross multiply. So I'm going to get mu k cosine theta plus sine theta is equal to 9 mu k cosine theta minus 9 sine theta. I'm solving for mu k, so I'm going to subtract. Well, actually I'll take it over here because there's 9 over here and 1, so I'll take it on that side and I'll take this to this side. So I'm going to get 10 sine theta is equal to 8 mu k cosine theta. And so that gives me mu k is 10 over 8, which is 5/4, times tan theta. Well, tan 30 degrees is 1 over root 3. So that's our value for the kinetic friction coefficient in this problem.